Okay, so this video is a bit different than the others. The others focus on things that you have to know, things that you need to learn. This one focuses on how you answer a particular type of question in the GCSE chemistry exam. It's dealing with the properties questions. Now, I'm not going to teach you why and how all these properties work. What I'm going to do is give you the basic way of dealing with these questions. It probably won't get you every single mark on every single question, but if you've been scoring very few or 0 marks on properties questions, then after going through this video a few times, you should safely always get about 2 out of 3 or 3 out of 4 marks. Prior knowledge for this is important. If you have not watched and understood the types of bonding video, you need to go back and do that, because without that you cannot even start attempting these questions. Okay, now in my experience, the properties questions in the C2 module are one of the questions that people dread the most. They're generally worth quite a lot of marks. It could be anything up to 1/6 of the paper. They appear really difficult, and though it looks like there's tons and tons and tons to learn, actually when you break these questions down and you look at how they vary from year to year, they are highly repetitive. As a result, they're really predictable. So if you learn the basic way of dealing with these questions, you should always be able to pick up most of the marks. And remember, on these papers, if you're picking up half the marks on each question, you're going to pass easily. Okay, so how do we deal with a properties question? There's 3 steps. The first and the most important is what type of bonding is present. Are we dealing with an ionic, a metallic, or a covalent material here? Once you've got that, look for what the question is actually asking. Okay, which specific property is it which they want to know about? If you're given the wrong one, you're going the wrong way. And then actually attempt it. But until you've worked out what the bonding type is, there is no point in going anywhere. Now this table is going to look quite scary, but when you actually get down to it, the information in it is really quite easy to understand, as long as you know your types of bonding. So if you've watched the last video, you'll know that an ionic bond has a metal and a non-metal. A metallic bond is a metal or more than one metal, and covalent ones are made of non-metal atoms only. Now there's the tricky bit. How do you know if it's a simple one or a giant one? Actually, that's quite straightforward. There's only 2 giant ones that you're likely to get asked for, and they're both carbon structures. So if you get diamond or graphite, or on a very rare day Buckminster fullerene, it's giant. Now they're generally easy to spot, because when they give you the question, they'll give you a picture of it, and if you're dealing with something that is a solid or is large and has a really complicated looking structure, it's going to be giant. If you're dealing with something that's a gas or a liquid and looks very simple, it's simple. This will become more obvious when we go through some questions. Okay, so the first bit of information for each. Now this comes straight from the last video. So ionic bonding is a lattice of positive and negative ions held together by electrostatic attractions. Okay, it's a long sentence, lots of big words, just learn it. If you learn that sentence, you're going to get marks. Okay, simple covalent. Simple covalent are small groups of atoms held together by shared electrons. Again, learn that properly. The words are all important. The shared word is often a mark on its own. If you got shared electrons in a question about covalent molecules, you're going the right way. Giant covalent is basically the same, except it's large numbers of atoms. Now I've put covalent bonds here, but we could have said held together by shared electrons, because that's what a covalent bond is. And finally, metallic bonds are lattices again, but this time just positive ions surrounded by delocalized electrons. Okay, so far so good. Right, now we're looking at some words that you might find in the question. So if it's a question about things like malleability, if it's ductile or not, if it's slippery, then we know what we're dealing with. Okay, first of all, you're not going to get a question about ionic bonds being malleable, because they're not. You're not going to get a question about simple covalent molecules being malleable, because they're not. The only ones you're going to get, if it's malleability or ductileness or slipperiness, are specifically graphite in the giant covalent group or a metal. And when you look at the reason behind it, you'll see it's exactly the same. Both graphite and metallic bonding have layers of atoms that can slide over each other. Now that means you don't actually have to learn very much. All you've got to learn here is, well, it's a question that asks about malleability. The answer is going to involve layers of atoms that slide. Once you've got that far, the question has gone from being a quite complicated analysis question to a simple memory test. Okay, so let's look at another property. Melting or boiling points or solid liquid gas questions. In other words, you might get a question along the lines of, this chemical is a gas. Why? Okay, if you see the word gas in a question, it's going to be this kind of thing. If you see a question about a melting or boiling point, it's going to be this particular kind of thing. Now again, we'll go through the answers and then look at the pattern. So, ionic bonds have strong electrostatic forces, which give high boiling and melting points. Simple covalent molecules have weak intermolecular, that word is critical, and these forces give low melting and boiling points. Giant covalent ones have strong covalent bonds, and metallic ones are strong electrostatic forces again. Now, let's look at how this works. Ionic compounds are basically all going to be solids at room temperature. Things that have high melting or boiling points and therefore are solids are likely, well always in fact, going to have strong bonds. Look, strong, strong, strong. In fact, if you get a question about why is so and so a solid and you say it has strong bonds, you're probably on the right way of getting the first mark. Okay, so strong forces give high melting and boiling points. Now all you have to think about is the type. It's an electrostatic force if you've got charges, in other words metallic or ionic, and if you haven't, it's just a covalent bond. Now the odd one out, the simple covalent molecule. Now, even if you don't know if something's a simple covalent molecule, there's an easy way of working it out from the question. If you get a question like, why is methane a gas? Well, why is methane a gas? Because it's a simple covalent substance. The only thing that could be a gas out of this list is a simple covalent substance, so it must be that. And the magic phrase is weak intermolecular force. If you use that phrase, you're going to pick up marks. Again, possibly not every single one, but enough to make a difference. Okay, the final one. Conducting electricity. Now, again, you're not going to get a question about simple covalent molecules and conducting electricity, because they don't. Now, if you look at the other answers, they all have some link. They've all got things that have charge. Delocalized electrons obviously have charge because they're electrons. So that's where you have to be thinking. And now it's just a case of what. So the two easy ones. Giant covalent, and again only graphite in this case, and metallic bonds both have delocalized electrons. It's electricity, it uses electrons. It's a fairly easy one to remember. So if you say that, you're going to get marks. So if you asked why does graphite conduct electricity, because it has delocalized electrons, and if you want to be flash add on this bit, that can carry charge through the structure. The only one you might get where this goes a little bit different is if you're asked why ionic substances conduct when they're liquid. It's still charge, but it's not an electron anymore, it's the whole ion. Ionic materials do not conduct when they're solids because the ions can't move around to carry the charge. However, as soon as you melt it or put it in solution, they can move, and then you've got something which can conduct. Okay, so let's look at some example questions. This is definitely the best way of seeing how repetitive these are. For each of these questions, I'm going to bring the question up on the screen, and then I'm going to leave a gap so that if you want to, you can pause the video and try and answer the question yourself before seeing the answer. So here's the question. Graphite is softer than diamond, explain why, and here is a picture of a diamond with its structure, and here's some graphite with its structure. Okay, so that's enough time for you to think about that, and hopefully you've had a go at it. Let's have a look at how I would answer this. Right, well, my first thought, graphite and diamond, they're both made of carbon. You need to know that. That's one of the main facts in the syllabus. If we look at their structures, they've both got a lot of atoms in them. So what we're probably dealing with here is a giant covalent structure. Okay, that's not answered the question yet, but I would always put that as my first statement. So both are giant covalent structures. But graphite, as we can see in this diagram, has layers. Layers can slide over each other, which makes it soft. And then finishing off the question, diamond does not have layers. It's important that you put that second statement in, because otherwise you haven't really compared the two, you've just spoken about one. Okay, so in an exam that might be 3 marks, possibly 1 for the type of bond present, and then the concept of sliding layers in one and the absence of them in the other. Okay, question number 2. Again, I'm going to pause this so you can try it yourself. Copper is a good conductor of electricity. Explain why. Okay, so again, that's long enough for you to have had a try if you've paused it. If not, here comes the answer. Right, first thoughts, we are dealing with copper. Copper is a metal, therefore we are dealing with metallic bonding. First thing to say, copper has metallic bonding. Now, we know we're talking about conducting electricity. Electricity almost always involves electrons, and we're dealing with delocalized ones because it's a metal. So, copper has metallic bonding with delocalized electrons. Now, why can it actually conduct well? Because these can carry the charge through the structure. Didn't actually have to know much about copper for this. All I've done is think back to that table. I've gone, it's a metal, so it's metallic bonding. Metallic bonding has delocalized electrons. Well, I've almost answered the question already just from those 2 facts. Example number 3, here it comes. Why is carbon dioxide a gas even at low temperatures? Okay, again a pause for you guys to try and answer that. And hopefully by now you've got something like this. So again, the first thing I do is I go for the type of structure. We have carbon and oxygen, both non-metals, so it is covalent. Now we know it's a gas, it tells us that in the question. If it was a giant covalent substance, it wouldn't be a gas, so it can't be that, it must be the other one. So carbon dioxide has a simple covalent structure. Always say what the type of bond is first. Right, now thinking back to our table from the beginning, anything which is a gas and is covalent has weak intermolecular forces. And then, even if you'd stop there, you'd probably be on half the marks. Just adding the last bit for polish, weak intermolecular forces are easily broken even at low temperatures. There's your rest of your marks. Okay, one more. Now on this one, we're being a bit tricky. Silicon dioxide is used for lining furnaces. Explain why. And we've got a picture of a silicon dioxide structure. Okay, so why is this one tricky? Well, silicon dioxide is not in the syllabus. It's not one of the standard molecules you expected to know. However, they've given us enough information to make a educated guess at it and work it out. It's also tricky because silicon is kind of a metal and a non-metal. It sometimes conducts, it sometimes doesn't. It's right on the line of where you would sort of define a metal or a non-metal. So we can't use our sort of normal approach. However, there's one big hint here. We've got a structure. That structure immediately tells you that it's not ionic because there's no charges in it. What we have are atoms joined by little lines, and those are always covalent bonds. So first of all, clearly covalent. Secondly, it doesn't look simple. It looks like a big complex structure. So we know what type of structure we're going for. It's a giant covalent structure. Now, it's used for lining furnaces. Well, it's not going to be put lining a furnace if it melts easily. So obvious answer, it's a giant covalent structure with a high melting point. Well, that ties in because giant covalent structures always have high melting points. Now we just have to explain why. Okay, it's a high melting point, therefore we are dealing with a strong bond. We know it's covalent, so it's a strong covalent bond, and they require a lot of energy to break, which is why they don't melt easily. We've answered the question. Most of the information we needed was actually in the question. If we'd worked out from here we've got a giant covalent structure with a high melting point, which is obvious from the question, we're over halfway to answering that, and we probably would have most of the marks. Okay, so example 5. Here it comes. Copper can be drawn into wires. By referring to its structure, explain how. Now this one is often messed up because people start giving long detailed explanations for how you could stretch a wire. The question is asking you to refer to its structure. You must talk about the structure, the atoms. And what people forget is drawing a diagram is perfectly acceptable. So what I've done here is draw a diagram showing metallic bonding. I've got my positively charged atoms, I've got my delocalized electrons around the outside, and I've added a couple of arrows to show that these layers can be pushed sideways and slide over each other. Just to make it absolutely clear, I've also written that down. That diagram on its own would get most of the marks for this question. So hopefully what you've seen is that these questions don't actually require vast amounts of knowledge. There's only maybe a handful of sentences you need to be able to throw at the most common questions, knowing the magic phrases like the weakens molecular force, the delocalized electron. And once you start realizing that the important section of this question is actually the property, not the chemical, it becomes so much easier. So go back over this, make sure you know those explanations, the simple explanations for each of the major properties you're going to get asked for.